Hey guys, and welcome back to the lab. In the last few weeks we've been working hard on LabStore with a few new features and a lot of refactoring. In fact, I have refactored the authentication package twice already, but I believe it's in a good state now. And that's what we're going to cover today. Join me if you want to learn how to implement AWS Signature version 4 both in theory and in practice through LabStore's implementation in Go. Stick around if you want to learn how to handle request signing with SigV4. So first let's try to understand what SigV4 is. It's AWS Signature version 4 and is used to sign requests. Every time you do a request to AWS S3 or any compatible S3 object store, you are using SigV4. And how does it work? The authorization header is used for signature exchange, so the client sends an authorization header and needs to compute SigV4 client side to send to the server, and then the server recomputes the signature and checks whether it matches. Computing it requires a secret key, user password, or a secret key from an access key, and requests specific elements as input, and we'll get to those in a minute. And then we compute a chain of signed hashes to produce a final signature. This is called HMAC, which is hash-based message authentication code. For SigV4, HMAC uses SHA-256 for hashing, and as I just told you, received and computed signatures must match. This is from the point of view of the server. Then we have streaming requests, which are special case. So for instance, if you have a put request that is uploading a file, an object, into the object store, this is a streaming request, and this is done in multiple chunks. This is to avoid a memory usage explosion. So it limits the maximum amount of memory that is processed at a time. And this also uses SigV4 for each individual chunk. So each one is signed. It's almost like a blockchain because the next chunk will always use the signature from the previous chunk when HMAC is being computed. And let's see how we sign streaming requests. So first we compute the seed signature, which is just using the standard SigV4 algorithm. So every time you have a request that is a non-streaming request, you'll run standard SigV4. You'll sign your request. For multiple chunk requests, you'll take this standard signature, just exactly the same way as you did for other requests, and you use it as the seed signature for the first chunk. So this will be taken as the previous signature for the first chunk. And then we repeat this process for the following chunks, always based on the previous signatures. And streaming ends when there is a signed zero size chunk. This marks the end of transmission. So now let's take a look at the spec. First of all, trust the spec. The official AWS S3 docs have all that you need. The standard single chunk SigV4 algorithm, which is here. Let's take a look. And as you see, they've got this diagram that explains everything in detail, and I'm going to go through all of this with you, but be sure to check the documentation if you are implementing this. Always have the documentation open and check it as you go. Most of the debugging must be done manually, so you'll need to make sure that you are producing exactly the canonical request or the string to sign as described in the documentation. And we also have the docs for streaming in multiple chunks over here. And this is very similar because this matches the standard SigV4, which is used to compute the seed signature. But then if you scroll down a bit, you've got the spec for how to compute this for each chunk as well. Again, we'll go through this. So for single chunks, the server-side steps are as follows. First, parse the canonical request. Then build the string to sign from this canonical request and other elements. Then you can compute the signature. There are several steps to this as well. And you compare the received signature with the recomputed signature. If they match, then the request is authorized. So a canonical request, which is the first element that we need to parse, looks something like this. So you've got your HTTP method on the first line, followed by a new line. You've got your canonical URI, which corresponds to the path, and this must be normalized and URI encoded. You've got your query string, single line query string, same order as received. You've got your headers, key and value. Each of those will be URI encoded. Then you've got a list of signed headers. These are separated by a semicolon. And finally, you've got your payload hash, your body hash, which is a hash for the file that you just sent, or whatever the body of your HTTP request was. So we've got our HTTP verb. The parentheses after each element that I add here is the name that they are using in the documentation, just to create a match. But we try to use a more clear language, a more technical language, and this is the HTTP method, right? And this can be get, put, post, always in uppercase. And as I'm going to show you these slides, I'm going to fill in an example for each of the topics that we are covering. So for instance, for path, and they call this the canonical URI, you essentially split by slash, and then you URI encode each element and join it back. So you get something like this. For instance, this would be a put to bucket in my path for file name parentheses 2, right? And this is URI encoded, and this is how you compute the canonical URI. Always add the new line over here. Then you've got the query string. It's a single line with all the query parameters, and you've got URL encoded keys and values, and it follows the same order as the original. So it can be something like key 1 equal value 1 and key 2 equals value 2, new line, right? Then you've got our headers, and this one is a little different because you can see here there is an extra new line, or apparently there is an extra new line, but in fact each header is defined as lowercase name for the header. So you've got the lowercase header name here, and then you've got the value colon and the value for the header as it was transmitted, and you've got a new line here, right? And then you have the same thing again, a new line, same thing, a new line, and all of this header block also ends with a new line, which is the new line that you see here, right? So you end up with something that looks like an extra new line, but really is just a marker that ends the header block. Then you've got the list of signed headers, and if you notice, this list includes host, but this is not a header that was sent, and the host will match the host of the server, so this doesn't need to be sent as a header. And then you've got semicolon and each one of the headers that were signed in the same order as they appear here. And finally you've got your body hash, which is called hashed payload, and this is always SHA 256. Sometimes you can have an unsigned payload, and instead of the hash you'll get this string, or if you are doing streaming, multiple chunk uploads, for instance, then you've got this streaming AWS HMAC SHA-256 payload string instead of the body hash. Then we can build the string to sign, and one of the elements, as you can see, will be a hash for the canonical request we just computed. But first we have this AWS HMAC SHA-256 string, which marks the beginning of a string to sign in SigV4. Then you've got an ISO 8601 timestamp. You've got your scope, and I'll tell you about it next, and you've got your canonical request hash. So like I said, we add this string to initiate the string to sign and a new line. Then we've got a timestamp in ISO 8601. As you can see, there are no dashes or colons separating the hours, and it ends with a Z. There is also a T in the beginning of the time in here. Then we've got our scope. The scope is a special string made by the date, the region for your object store. It can be something like EU West 1. The service, it will almost likely be S3, and AWS for request, which marks this as being SigV4, I believe. And then you would get this. And finally, we can add the SHA-256 for the canonical request we previously computed. If you wrongly computed this canonical request, it will be hard to detect an error here, and this is where debugging this can become quite complex. Finally, we compute the signature. This is computed using HMAC SHA-256 based on the secret key that you already know. It's your password or from your access key, the scope date, the scope region, the scope service, the scope request type, and the string to sign that we computed in the previous step. So this is an example directly from the docs where we are using this HMAC SHA-256 function that takes a key and the value that we want to encrypt. And so we do this in several steps. First, as our key, we use AWS4 and our secret key. We concatenate this, and then we give it the scope date, and we compute HMAC for this. Then we take this result and use it as the key of the next call to HMAC, and this time we encrypt scope region. Again, we take the output and use it as the key to encrypt scope service. Same with AWS request 4, and finally this is our signing key, and we use this to sign our string to sign. And finally we get the final signature. We compare those two, and if they match, the request is authorized. Now, for multiple chunks, for streaming requests like put object, which sends multiple chunks, these are signed as usual, and then they are signed per chunk, like I told you before. Like I said, again, it's similar to a blockchain somehow. Each chunk includes the previous signature during signing. And requests that are streaming requests are identified by the special payload hash that I showed you already before, and this is also set as the value for this header, XAMZ content SHA-256. So each chunk has a header with the X value of bytes to read along with the signature. It's a very minimal header, but of course we've got an example here of 10k bytes in X, which is really 566 bytes. So take care that this is X, so you need to convert this to decimal. And then we've got the chunk signature, which is SHA-256. It's always, every time you've got an hash, This is an SHA-256. It might be, if you are using HMAC, you'll still use this hash, but it will take a key as well. And then we've got the number of bytes here, right? So an example of a string to sign for a chunk, these begin with AWS HMAC SHA-256-payload, and this is the suffix payload is the main difference. Then we've got the timestamp, the scope, like the standard SigV4, and then we add the previous signature. For the first request it will be the standard SigV4 signature, and for the next request it will be the signature from the previous chunks. Then we've got this hash for the empty string. This is some kind of control, I'm not sure why this is here. And then we've got the hash for the chunk data. As you can see, we add the timestamp, then we add the scope. This matches exactly what we did before except for payload. And now we add the previous signature. We add the empty string signature, which will always be this if it's SHA-256. And finally we add the chunk data as hash as well. Then we compute the signature using the same logic as standard SigV4, and we compare them and either validate the chunk or stop with some error. And remember that the last chunk must be a 0 size to mark the end of the stream. Now let's talk about how we implemented this in LabStore. So here let's take a look at the class diagrams. We've got our package level functions. We've got an auth package where we implement all of this, and we only have two public functions. One is for verify SigV4, which is for standard SigV4. This is always run on signed requests. And we also have this constructor for new SigV4 chunked reader, which for streaming requests will replace the body of our HTTP response with a custom reader that will validate each chunk and just return the bytes directly. Then we've got internal constructors to help us parse the request from an HTTP request to a SigV4 request, which is a structure that is more useful to us internally. And this also uses a SigV4 authorization, which is part of the request, and a SigV4 credential, which is, I believe, part of the authorization. Then we've got a generic compute signature function, because it is used both by the standard SigV4 and the streaming version. For single chunk signatures, we've got these types, as I was saying. So our SigV4 request will contain the method, the canonical URI, which is the path, the canonical query string, the canonical headers, the authorization header, and this is parsed as the credential, an array of signed headers, and the signature that we received. And like you see here, the credential will include the access key. This is parsed directly from the authorization header, but internally we also fetch the secret key, which is on our database on our side, and we set the scope. Next we've got our timestamp, and finally our payload hash, which is our body hash. Then we've got this validate payload hash. This is optional because this might, lower performance, because the body hash is already included in the signature process. So this is just a wait for early failure if you want to be that strict, but at the cost of some performance. Then we have validate signature. which takes the result and recomputes the signature internally. Then we've got some helper methods like build canonical request and build string to sign. Finally, once we compute all of this, we return a SigV4 result containing the credential object, the signature that we computed, the timestamp, and whether this is a streaming request or not, which we know because we'll have access to this payload hash over here. And so for multiple chunk signature types, we've got our SigV4 chunk reader, which uses the SigV4 chunk header and SigV4 credential, which comes from the standard SigV4. This is just used internally, it's the same values like I told you before, so we just pass this object along. The chunk header, like I showed you before, it's just a size and a signature. This size is already in bytes when we parse it. And then for the chunk header, we've got our body, the original body. We've got the previous signature, the credential, the timestamp, our internal reader. This is the reader that we are going to use to keep track, to go through all the bytes as the user or the consumer of the replaced body reader is calling read. It depends on the buffer size. And then we've got our header and the chunk data, right? So we implement read and close because the body is a read closer, right? This respects the interface. And then we've got our read chunk header, we've got our read chunk data, read trailing CRLF, which is a part of each chunk. We verify the chunk signature, and we've got this helper method to build the chunk string to sign. So the workflow will look something like this. For instance, for a put request, which is a streaming request, but also includes the standard SigV4 signature, we will do that request from a client to our router. Our router will send the HTTP request to our middleware. One of the elements in our middleware is the AuthMiddleware. And then inside the AuthMiddleware, we'll ask to verify SigV4. We send it to the HTTP request, and this goes into the auth package, particularly into signature.go. And then signature.go will run the verifications internally and return a SigV4 result. Then this SigV4 result is checked, and if streaming is true, then we'll ask to create a new SigV4 chunked reader, which is defined on auth streaming, and we'll replace our body with this new reader, and go to the next handler until we get a response. The next handler will be any other middleware that comes after this, because our body, this auth SigV4 chunk reader, just returns the actual bytes for the uploaded file. This will be essentially transparent, right? It just controls error, it checks if the signature is valid, it returns an error if not, and if everything goes right, it will return as if nothing happened. And this is how we implement SigV4 from a theoretical standpoint on LabStore after refactoring this twice. But now let's go and take a look at the code. So now let's take a look at how this is implemented on LabStore. So I'm looking at the release backend branch here for 0.10. This is not complete yet, we are working on it. But as it stands, if you go into backend and if you go into internal, you find most of the implementation over here. And in auth, we've got our SigV4 implementation. We also have the AuthMiddleware over here, and we've got our router, which is the entry point. So for our router, as you can see, we are creating this middleware stack with AuthMiddleware over here, and we launch our HTTP server with the middleware. Let's go into AuthMiddleware, This is this file over here. If you look at AuthMiddleware, we are essentially just taking a request and running auth verify SigV4 with this HTTP request and checking for errors. If there is an error and the signatures do not match, by the way, this was an external contribution already, this error control over here, so thanks. It seems like there is some interest already. We still need to define the rules of contribution because we were not prepared to, to open to the outside yet. But this is quite welcome, and we hope to be open to contributions in the future. Although many of the tasks, many of the issues that we already have that are assigned to us, it's something that we want to implement ourselves, because this and Illumino Labs, the members of Illumino Labs are there to to learn something, me included. So some things we want to keep for ourselves because we want to learn how to do it, but as the project grows we'll keep opening it more and more to outside contributors. So thanks for the interest. And so, like I was saying, we verify SigV4 over here. If there is an error, we just return. Then if there is no error, we check if this is a streaming request. If it is a streaming request, then we replace the body reader by our custom SigV4 chunked reader. We send the HTTP request to it, and we also send the result from the verify SigV4, which contains several elements that we need, like the seed signature, or the scope, or the timestamp, or whatever. Once this process is fully validated, then we add the access key to the context of this request, and we continue processing with the next middleware. So the most interesting part for this is obviously inside the auth package. So let's take a look at that now. So in auth we've got a few constants for the special payload hashes, as well as for the signature computation function. This is very similar to what we just saw in the slides. There are just some details here with conversion to byte arrays, and we implemented our hmac function over here as well. It's a very simple wrapper, and so the most relevant files are signature and streaming. Let's take a look at signature. For signature, we've got the types that we showed you in UML in the slides with the class diagrams, and this is exactly what we just showed you. So verify SigV4 will take the request and return either an error or a SigV4 result. We wrap these errors with SigV4 as a prefix, so that we know that it comes from SigV4, and it's the only prefix that we use. I think it's more than enough. So this new SigV4 request will parse the HTTP request into a SigV4 request, you can see here. And if we go into this parser, we'll see that we are reading the authorization header, then we are parsing this authorization header, as you can see here, and we are doing all kinds of stuff like checking whether it begins with this prefix. Then we are removing it and splitting by commas, and then we are extracting the credential, the signed headers, the signature, and we are parsing the credential as well. Finally, we return this SigV4 authorization, and we go back here, right? And we keep parsing each header. So the case doesn't really matter here, so we'll match either way. And then we got our payload hash, our timestamp. We take our canonical URI from the path directly, and then we've got this build canonical URI that takes care of escaping. We do something similar for the query string. Okay, we query encode each part, and we also do something similar for the headers. If it's host, it's a special header. We get it directly from the request. And finally, we return this result with our SigV4 request. Now, SigV4 request implements several methods. One of them is validate payload hash, which we can call here to make sure that the hash for the body matches the hash that was sent. We also have the validate signature, which is the main method here. In here we build the string to sign. We go into the string to sign, we'll see that we build the canonical request, and then there is a string writer over here that writes everything that we just showed you before. We begin with this and a new line, the timestamp a new line, the scope and a new line, and finally the canonical request hash, right? With no new line. And I had a new line here before, and it took me like 2 days to debug this, so it can be a pain to to find the bug here, because there is no way to really trace it. You can just log each part and check whether the code is correct, but always trust the spec. The spec is correct, trust the docs are correct. And so we return the string to sign, and then we compute the signature based on the credential and the string to sign. And finally we compare the two signatures, the one that was sent as well as the one that we recomputed. We check whether this is also the signatures match, this is streaming, and we pass this along in SigV4 result, right? So essentially, once we do this in the middleware, we are at this stage and we are checking whether this is streaming. If this is streaming, then we'll go into the streaming file over here, and in here we've got our chunked reader as well as the chunk header, and this just creates an instance of SigV4 chunked reader. It's just more practical to to just send two parameters to abstract this than just to create this directly. So this is the result of a slight refactoring over here that makes this clearer. Then we implement read, and read is the main logic for this streaming module. So if our reader is nil, we instance a new reader for the body. We only instance this once. If there is data on the buffer that we read before, we will return that data. If there is data, it means we haven't sent all of the data for the current chunk to the upstream, right? And then we read the chunk header. If the header size is 0, it means we reached the end of file, right? We end our reading process and return EOF. Then if not, we read the chunk data, and this chunk data will be read. If we go into read chunk header, we'll see that we are parsing all of this, and then as you can see, we are converting from hex to decimal here, and we set this size over here, and this is how read chunk data will know how many bytes it needs to read, right? So we'll need a buffer of header size, and then we finally read a CRLF, which marks the end of the chunk. And finally we verify the chunk's signature. There's an error, the process will stop here. If not, we set the previous signature to the current signature, and this is initialized with the seed signature that comes from standard SigV4 for the first chunk. For the next chunks it will be the previous signature, and then we copy the red bytes into the buffer and return the number of bytes read, and remove those bytes from the current buffer. When the buffer is empty, we go to the beginning. The buffer is not empty, we return that data until the buffer is empty, and we keep removing that data over here, right? And that's pretty much how SigV4 chunked reader works. There's not much more to it. We've got the close method over here, perfectly standard, and all of these are parsing methods that are really helper methods. And other than that, in verify chunk SigV4, we use compute signature from the shared auth module, and that's it. We've got our build chunk string to sign over here, which follows the logic that we described before. There is a different string that marks the beginning of this string to sign, timestamp, the scope, the previous signature, the signature, the hash for an empty string like you see here, and then finally the hash for the chunk data. And that's how you implement SigV4 in Go. Hopefully this was useful to you and you learned a bit of how object stores that are S3 compatible work. So before going, let me just show you a quick demo of how this works. And so in debug mode, you'll see all the information that you need about SigV4 requests. And then on the right side, we've got a just file that we implement under backend. And we implemented a few test scripts. So we've got this test put obj mc. And this will just create a 10 megabyte file with random bytes and upload this into the object store. And as you can see, you can already find here several chunks being verified with a string to sign being computed here correctly. We redact everything that is a hash just to avoid leaking any key. If for some reason you are running this on debug mode and making a video about it with real credentials or something like that, or if you are logging this into an external service, then you'll be, safe to know that none of your credentials will be leaked. And somewhere over here you'll find a put request. As you can see here, there will be the authorization header. It sends the signature. There is a credential, there is the sign headers over here, there is the signature itself that we need to recompute and validate. And then we extract the header parts, we extract the access key from the credentials, which is admin, and we've got the password for admin in our system, right? Somewhere. For now it lives in an environment variable, but in the future we'll have a proper storage for that. We compute the canonical URI, there is nothing being escaped here. We compute the canonical query string, which is empty, and then we build the canonical headers. As you can see, it's a map containing a host. This will be another element, right? Then we compute the canonical request with all the elements that we saw. It's hard to read it on the logs, but you can use these logs, this kind of logs, to help you debug it if you need to. And then we compare the signatures. The signatures clearly matched, so it checks whether it is a streaming request, which it is, and it proceeds to create a new chunked reader and reading the header, the chunk data, the CRLF, building the string to sign, checking whether the signatures for this request are valid, and so on and so forth, uploading these small chunks until the whole file is uploaded to the object store. If you go and check and do an ls, we are uploading into the sandbox over here. If you do an ls to LabStore sandbox, you'll see that there are several files that I used to test, and this particular file was called sedi, tmp sedi, and I'm sure, yes, we can find it over here. So it was fully uploaded, right? I don't know if it is still available or not. It is not, okay, so, or otherwise I could compute the hash just to check that it was properly uploaded. But yeah, this is how you implement SigV4. This is how we are implementing SigV4 on LabStore. And if you find any security issue, let us know, please. But I believe this is correctly implemented. Now it's a matter of performance tuning, because obviously and particularly during uploads, this process will be extremely expensive because it needs to be processed sequentially. It cannot be parallelized, since the signature for the current chunk depends on the signature from the previous chunk, so it's impossible to parallelize this. And that's why there is multi-part upload as well as a separate feature that we do not support yet. But we will in the future, of course, and we are working on it. Out of curiosity, let's just introduce a slight bug over here. For instance, in the main signature one, when we build the string to sign, initially I had done something like this, and this is incorrect. The last element does not require a new line, cannot have a new line. And so now if we go into the command line and we exit this and recompile, see how fast that was? Let's go for you. And if we now try to put the object, then we'll get an error. The request signature we calculate does not match the signature you provided, right? So signatures do not match. Because, you know, I introduced an obvious error, but this is what happens when there is a wrong credentials or something like that. And there you have it. I hope you found this useful, so you can now implement your own SigV4 authentication. But if you don't want to, remember that there is always LabStore, our free and open source S3 compatible object store in the making. We're currently working on the post request for batch deletions and bootstrapping the web UI, so that's where we are currently. Once we're done with that, for the next video, we'll focus on performance. We'll set up other open source object stores on our home lab and run the warp benchmark to test them. So you'll see about all the existing competitor object stores in the market, or open source in this case, and we'll also compare them performance wise in a similar scenario. And then we'll do some Go profiling on our end to try and squeeze a little more performance out of LabStore, just to see how far Go can take you in a world of high performance Rust, right? I believe we can go really far with Go. Maybe not as high performance as Rust, but we can also go faster, right? As usual, this week's blog post is available at datalabtechtv.com. Follow the channel on Blue Sky for updates, and join Discord if you have any questions. Don't forget to drop a like and subscribe for all things data.